Good morning, everybody. Welcome to the video lecture on fundamentals of alternating current. In this lecture, we will be seeing what is an alternating current, how can we generate it, and what are the different parameters that are used to measure the alternating current. So, first of all, what is an alternating voltage or an alternating current? So it is an voltage or current that varies both in magnitude and polarity with respect to time. For example, consider these waveforms. So these are some waveforms representing different voltages. So in the first case, we are having a sine waveform. Here we can see that the magnitude is changing as well as the sign is also changing, that is polarity is changing. Here we are having a positive voltage and here we are having the negative voltage. Same case with the second waveform. Here also the magnitude as well as the polarity of the waveform is varying. Here in the case of triangular wave as well as the square wave, we can see that magnitude is sometimes positive, then sometimes it is negative. So magnitude is changing as well as the polarity is changing. So all these four are the examples of an alternating voltage. Then take a look at this figure. Here we can see that the magnitude is changing. In all these figures, the magnitude is changing. Here also, in the case of a triangular wave, magnitude is changing from 0 to 1. And the second case, here the magnitude is also varying from 0 to 1 volt. But what about the polarity? The polarity is always positive. All the magnitude is having a positive value. So this is not an alternating quantity or an alternating voltage. Instead, we can call this as a varying DC because direction is not changing. In the case of an alternating quantity, the direction must change. That is, the polarity must change. Next, we can see the generation of alternating voltage. A sinusoidal voltage can be generated either by rotating a coil in stationary magnetic field or by rotating the magnetic field by keeping the coil stationary. So consider this figure. Here we are having a single loop conductor. This conductor is placed in between a pair of magnetic poles. So the magnetic field lines will be directed from the north pole to south pole. The coil is rotated in anti-clockwise direction in this magnetic field. So when the coil rotates, it will cut the magnetic flux lines. So as a result, an EMF will be induced in this coil due to electromagnetic induction. And this is a dynamically induced EMF and it is given as, magnitude of this EMF is given as E is equal to BLV sin theta. So magnitude is E equal to BLV sin theta, where B is the flux density, L is the length of the conductor, V is the velocity with which we are moving the conductor, and theta, that is the angle between the flux lines as well as the conductor. Next, we can see what is the nature of this EMF generated. So we have already seen that the induced EMF, that is E equals B L V sine theta, right? This is your induced EMF. B, L and V is a constant, so that we can write it as EM sine theta. So here we can see the induced EMF will vary sinusoidally. So that is why the single phase generated voltage is an alternating quantity which is sinusoidal in nature. So here we can see the different position of the conductor as well as the nature of the EMF generated. So at position A, the angle between the flux lines and the conductor is 0. That is theta value is 0, so EMF generated will be 0. And at position B, the angle between the flux lines and the conductor, that is 45 degree. So EMF generated will be EM sine 45 degree. Then at the position C, the angle between the flux lines and the conductor is 90 degree. So the EMF generated, that is EM sine 90 or EM, that is your maximum value. So by completing one cycle or one rotation of your conductor, we will be getting one cycle of the sinusoidal waveform. That is explained in this figure. Next, we can familiarize with some of the parameters that are used to measure an alternating quantity. First parameter is instantaneous value. So what is an instantaneous value? Instantaneous value is value of an alternating quantity at any instant of time. So consider the given sine wave, which is represented as A of t equal to Am sine omega t. Instantaneous value can be obtained by substituting different values for t. For example, the value of the sine wave at t equal to 0, that is A of 0 will be equal to Am sine 0. We know that sine 0 is 0. That is instantaneous value at t equal to 0 is 0. Similarly, the instantaneous value at t equal to omega t equal to pi by 2, that will be equal to A of t will be equal to Am sine pi by 2, or A of t will be equal to Am. Here we can see that the maximum value is kept as 1. So instantaneous value that can be obtained by substituting different values of t. Next parameter is cycle. So cycle is one complete set of positive and negative values which repeats at regular interval of time. So waveform that is repeating, the shape that is repeating, that will represent the cycle. So this is a cycle, a complete set of positive and negative values. Next parameter is time period, and usually it is denoted as t. So time period, that is the time taken for an alternating quantity to complete one cycle. So for the given waveform, this is a complete cycle. So here we can see that the time taken to complete the cycle is 2 pi radians, or the time period will be 2 pi. Next is frequency. Frequency is number of cycles of the alternating quantity in 1 second. The unit of frequency is hertz, and the frequency can be obtained as F is equal to 1 by t. Another important parameter is phase of an alternating quantity. Let's see what is a phase. The phase of an alternating quantity is the fraction of time period that has elapsed since selected origin. Okay, so consider the following sinusoidal waveforms. In the first waveform, assume that a selected origin is when the sine waveform is 0 point of the sine waveform. Okay, and we are measuring the phase at t equal to 0. So at t equal to 0, we can see that that point coincides with the selected origin. So here we can say that time elapsed after the selected origin is 0 at the given time instant. So here phase is 0. Why? Because your selected origin and the time instant when we are calculating the phase is coinciding. So your phase is 0. Then consider the next figure. Here your selected origin is this point where your waveform is starting. And we have to calculate the phase at t equal to 0. So here we can see that 5 degree plus 5 degree has elapsed since the selected origin. So here the phase is positive and that is equal to plus 5. Then what about the third figure? Your time instant where we have to calculate the phase is t equal to 0, but the selected origin that is coming after this time instant. Here this is your selected origin and that too the shift is 5 degree. So since the selected origin is coming after your time instant, here the phase is negative. So here we can see how the waveform can be written. First case your phase is 0, so A of t is written as Am sine omega t. In the second case, we are having a positive phase. That means your sine wave is advanced. So we can write A of t as Am sine omega t plus 5. The waveform is having a positive phase. Then in this case, the waveform is delayed by an angle phi, or we are having a negative phase. So our waveform will become as A of t is equal to Am sine omega t minus phi. Then another term is phase difference. The phase difference is usually calculated for two waveforms having same frequency. So phase difference is if two alternating quantity of same frequency have different 0 points, then they are having a phase difference. So phase difference that will be calculated between two alternating quantity, requirement is that they must be having same frequency. The magnitudes may be same or may be different. So take a look at the following figure. Here I am having two sinusoidal waveform. One is representing your current and the another one is representing your voltage. We can see that the magnitudes of these two waveforms are different, but the frequency is same. In the case of these two waveforms, both the waveforms have same 0 points. Here at t equal to 0, at t equal to pi and at omega t equal to 2 pi, we can see that both current and voltage waveform are becoming 0. That means the phase difference is 0 because Phase difference means the phase difference occur only if they are having different 0 points. But in this case, both the waveform is having same 0 points. So here the phase difference is 0, or we can say that both voltage and current waveforms are in phase. Now we'll take a look at these two waveforms. Here also we are having this a voltage waveform as well as the current waveform. Okay, but what about the 0 points? The voltage waveform is becoming 0 at t equal to 0. But the current waveform is becoming 0 only at omega t equal to 30 degree. So here we can see that there is a phase difference. There is a difference in 0 points of both the waveform. Here we can say that the current is lagging the voltage by 30 degree, because first the voltage becomes 0, then after 30 degree the current is becoming 0. So current is lagging your voltage, that is delayed by an angle 30 degree, or the phase difference is 30 degree. Or in another words we can say that voltage is ahead of current, right? So voltage is leading current by an angle 30 degree. So the parameter which becomes 0 first, that is the leading quantity, and the waveform which becomes 0 later, that is known as your lagging quantity. Next is average value. So by definition, the average value of an alternating current is that steady state current which transfers the same charge across an circuit as that is transferred by alternating quantity. So here we can say that it's actually the DC equivalent of an alternating current. So it's a DC value of the current which can transfer the same charge as an AC current. Mathematically, average value is equal to area under the curve, that is area under the waveform by time period, or the average value of any alternating quantity V of t is given as V average is equal to 1 by time period integral 0 to t V of t dt. So average value that is calculated for a complete cycle. Next parameter is RMS value. So RMS value, or the root mean square value of an alternating quantity, is the steady state current which when flowing through a given circuit that produce same heat as produced by an alternating quantity. So this is the DC equivalent which can produce same heat, that means which can produce same power loss as an alternating current. So RMS value of AC, that is usually calculated when we need to find the power consumed by the electrical circuit. So this is which produce same heating effect is same. So mathematically RMS value of any alternating quantity V of t is given as Vrms is equal to root of 1 by t integral 0 to t V of t square dt. Root mean square value. Okay. Next two parameters are form factor and peak factor. Form factor, that's the ratio of RMS value to the average value. That is form factor Kf is equal to RMS value by average value. And another one is peak factor, that is the ratio of maximum value, peak maximum value to the RMS value. The peak factor, that's also known as amplitude factor or crest factor. So peak factor, that is usually denoted as Kp, that is equal to maximum value by RMS value. So we come to the end of video lecture on fundamentals of alternating current. In the next video lecture, we can see some numerical related to this topic. Thank you.